Hello and welcome back to Calculus 1. We have 4.5 now, the optimization problems. These are going to be the applied problems, i.e. word problems, right? Where you minimize and maximize functions. You want the maximum profit, minimum cost, maximum volume, minimum surface area for object and so on to reduce the cost of making it and so on. So a lot of opportunities to cash in on this section. The major that we have here geared specifically towards the Rutgers packaging engineering, this is one of the central sections because, as I said, you deal with volume and a surface area for the box, and you want to make sure that that is optimized because you want to save as much money as possible to reduce the cost. So let's first talk about the idea of a min-max. Say, find two numbers with sum 36 and maximum product. So, can you find easily two numbers that add to 36? Yeah, you don't have to think about it too much, like 35 plus 1 is 36, right? You're done. But what's the product? So 35 plus 1 is 36. We're good there. But what's 35 times 1? Is 35. Now, 34 plus 2 is also 36. But look, 34 times 2 is 68. That's much bigger than 35. Do we all agree? Hopefully we do. And then you say, okay, how about 33 plus 3? Because that's also 36. And the product is now 99. So now you go and you try to figure out what values, right, you get to add into 36. Now, there's not that many of these, right? You'll go through 36 combinations and then you will actually figure out going through the entire table, but it's not too efficient, right? So is there a mathematical way to deal with this? And the answer is yes. We can just say two numbers, I don't know what they are, but I know they add to 36. So how do I write sum of two numbers is 36 in mathematics?
X plus 36 minus X.
Sum of two numbers is 36. What you gave me is the something else. Yes?
Like X plus Y, 36?
Yes, X plus Y equals 36. So this is the way to say sum of two numbers is 36. I don't know what the numbers are. I'll call one X, I'll call the other one Y, and that's it. And now I need a maximum product. How do I write that? What is the meaning of product? What is product? So, X times Y equals a max. So, what I have here is the mathematical model for this problem. I have a sentence, find two numbers with the sum of 36. Sum of two numbers is 36. X plus Y equals 36. Product should be a maximum. X times Y is a max. So now, in the language of our section 4.5, this particular equation is called constraint. And this is the objective equation. So constraint and objective. Objective is what you're trying to achieve. You are trying to maximize the product. And under the constraint that numbers have to add to 36. Does that make sense? It's like when you're going to the airplane and you have the constraint of the size of the carry-on luggage. You can't take your big 30-pound suitcase into yeah, right? It won't fit anywhere. So the constraint for the luggage, carry-on luggage, has its, right? So you understand the word constraint. You know what it means. And you follow those constraints all the time. Red light, constraint. You're not supposed to move. Otherwise, you're going to get erased by a car coming in the opposite direction. I mean, perpendicular or intersection. So you understand the constraints. So you will be reading the word problem and you will be looking for that constraint. Now, every single problem in this section will have the constraint. And also, every single problem will have the other equation, which is what you're trying to achieve, your objective. In this case, you are trying to achieve maximum product. Now, again, this problem is just mathematical gymnastics, right? We are just explaining the procedure. We are going to do applied problems after this, right? So how do I solve this problem? Well, I have this equation here, objective equation, which has two variables. So I'm going to go into the constraint equation and solve it, say, y equals 36 minus x, and then plug in. So that's what we have. So now I have x times 36 minus x equals a max, which is 36x minus x squared equals a max. So this is my equation now. And how do I find the maximum? How do you find maximum? We already covered that in 4.1. How do we find max? (4.1). We took the derivative and we set it equal to 0, right? To find horizontal tangency. So if you have a max of some kind, the slope m is equal to 0. You know that slope is the first derivative. So to find a max or a min, you take the first derivative and you set it equal to 0. Well, the great thing over here is you don't have to set anything to 0 because you have a max on the other side. That max will turn into 0. See, because when you multiply two numbers, x times y, you're going to get some value which was your max. I don't know, 107, whatever. The derivative of that would be 0. So what we have is 36 minus 2x equals 0. 2x equals 36. X equals 18. And now I have y equals 36 minus 18, which is also 18. So what are the two numbers? They're actually 18 and 18. So x equals y equals 18 for max product. Now, if you continue the table of values and you go to 32 plus 4 is 36. 32 times 4 is equal to 128. Eventually, you are going to get to 18 times 18. And what is 18 times 18? 324. So you will see that as soon as you go to 17 and 19, 17 times 19 is also going to add to 36. But it's 323 when you multiply them. One less than this. So this is the procedure for all of these problems. You read the problem, and you come up with equations for that problem. One equation will be constraint, and one equation will be the objective. Objective equation is always the one that has min and max in it. You will always plug constraint into objective, eliminate one of the variables by doing that, and then take the derivative. So again, it's structured, but every problem seems different. So procedure: read and understand. Number 2, get constraint and objective functions. Number 3, plug constraint into objective to eliminate one variable. Number 4, differentiate equation number 3, set equal to 0. Number 5, solve number 4. Number 6, win. There you go. That's the procedure. It's always the same procedure. Read the word problem, set up the word problem, solve the result, plug one equation into another, solve the resulting equation, and you have your answer. So let's take a look at another Okay, so some of my favorite problems are the farmer problems. Farmer has fence, wants to fence off rectangular area, right? Pasture or a garden or orchard, doesn't matter, right? And some geometry is to be done. So you don't obviously want to go and put all of the posts and do the trial and error on this thing, right? If you have 2,000 yard of fence, you just want to fence off an area that it's maximum area, and you need to. So there are different configurations. So we'll see this. So this is farmer problems. So we start easy. Farmer has 2,000 yard of fence. He wants to fence off maximum rectangular area. Find the dimensions. Very simple. So, how do you do this? Well, you start by drawing the rectangle to understand the problem. You have lengths x and y, and you have to understand, this is where common sense kicks in, that the perimeter fence goes along the perimeter of the property, right? So, you know that the fence is going to go all around where this black line is. That's a perimeter. What's a perimeter for the rectangle? It's, you add all the sides, 2x plus 2y, and that needs to be Exactly 2,000 yard of fence that the farmer has. Yay, we already have our constraint. What does he want to do? He wants to fetch some maximum rectangular area. Maximum rectangular area, max area. XY is a max. Guys, this problem is exactly the same as the previous one we did with numbers, except now we gave it a context. Right? Earlier we had x plus y equals 36. What do you have now? X plus y equals 1,000. Right? It's the same problem, same solution. So from the top equation, x plus y equals 1,000, y equals 1,000 minus x, plug in. Now your x times 1,000 minus x is equal a max. 1,000x minus x squared is equal to a max. Hit this with the derivative to find the x value, and x equals 500. So the y will be 1,000 minus 500, also 500. So we just seen that the square seems to maximize the area. So dimensions are 500 yard by 500 yard. It's a square. Previous answer was 18 times 18. Now it's 500 times 500. Any other combination would give you less in the area. There are many combinations in which you can, put your fence, 2,000 yard of fence, to close off an area. But only one of those is going to be the most optimal way to achieve a maximum. So now, as we push on, we modify this problem to, other things that the farmer might run into. And that is should be applause in the middle. Have to deal with me every day. So let's take a look at other situations that might arise. Let's say you have this pasture that you want to just put a sheep in, right? One side has a river. No need for fence. So all you have to fence is 3 sides. Way to solve this problem is the same, except now your constraints change a little bit because you have a single x and 2 y's. So now it's x plus 2y is equal to 2,000, and x times y is still a max, and it's still the same thing that you have to do, except now you are not going to get a square as the answer. You are going to get actually a rectangle this time around. So by changing the configuration, the resulting geometry would change. So now you have the river. Maybe I should put some salmon in. Here. Bam. Salmon right there. Now it's clear it's the river. So go on, calculate. Tell me the dimensions, x and a y. Now in this case, guys, it's easier to solve for x, right? To get y first, because if you go y equals, you will have to deal with fractions. If you go x equals 2000 minus 2y, then you don't have to deal with fractions. So go from there. Start that x equals 2000 minus 2y, and then plug in, and you will get y first this time around. When you get y first, you can calculate x later.
I should plug this mix on the. It is just fine. Yeah?
It's a trig one, unrelated to the problem. You know that one? From trig class. Look, just cancel in. Okay, it's a trig identity. 6 equals 6. Right?
Can you scroll back up on that?
Shoot. How far? As the
Oh, yeah. Wow. Can you explain why again we get 2x plus y, 2y equals 2000, and then you arrow down to x plus y equals 1000?
I divided by 2 everywhere, right? If I divide the entire equation by 2, everything, you lose 2 in front of x, 2 in front of y, and 2000 divided by 2. I divided it by 2. Reduce the equation, right? Now we can't do that because we don't have 2 in front of x.
Right. Okay.
So we are stuck with what we have. So now instead of x, we have 2000
Gotcha.
minus y. Everything times y. No, 2002y. There you go. Equals a max, and then you distribute, differentiate, solve. Let's go.
asking for the dimensions of.
Yes, x and a y.
Okay.
Okay, so that's 2000y minus 2y squared equals a max. We differentiate. We get 2000 minus 4y equals 0. Y equals 500 yard. But now when you plug in 500 into x, you will get 1000. So x equals 2000 minus 2 times 500 is 1000. So now dimensions are 1000 by 500 yard for the configuration when the river is there. Say that farmer has to separate things, create bins. Say that situation is like this. Cabbage, rabbits, and tigers. Can't put them in the same. Tigers are gonna shred the rabbits. Rabbits are gonna eat the cabbage. Can't put them all in the same, right? So you separate them. So now I have dimension x and dimension y. I still have 2000 yard of fence. I still want max area, but I need these bins like this. So fence is spent on that as well. What is your constraint now?
You just add more of the y variable.
Very good.
Yeah.
You have 4 y's now.
Yeah.
Yeah. So now we have 2 x's, one on top, one on the bottom. Right? Those are the horizontal ones, plus 4 y's. For the same 2000, it has to fit in 2000. And you still want xy to be max. That doesn't change because you want the maximum area. So now from the top equation, your x plus 2y is equal to 1000. From where x is equal to 1000 minus 2y, plug in, and you get this symbol now. Just do it. Let's say I'm going to put a lot of stuff out there, but I need a small corner. So let's say everything is orchard and I just have a small corner for a garden, like this. And you have your x, and you have your y, and then you have your x over 2, and then your y over 2, let's say. The other way around. Y over 2 on this side, and x over 2 this side. You still have 2000 yard of fence. Still want max area. What are the dimensions? What's your as soon as I say max area, that's xy equals max. The objective function is the same. What's the other one? What's the perimeter one?
The perimeter function for that?
Mm-hmm.
It would be 2x plus 2y
Good.
plus y over 2 plus x over 2.
Yes. Very good. No. Yes. Equals 2000. Yes. Mm-hmm. Because you have extra 2 lines, right? Without the inner part, you just have 2x plus 2y. So 2x plus 2y on the outer rim is 2x plus 2y. But now we have the inner one over here. This is y divided by 2, and this is x divided by 2. That has to be added as well because that is physical fence that we have to put up. Because we want to separate the garden from the orchard, let's say, right? Or you put the tigers in here and rabbits in there, right? So whatever. It's all about figuring out the geometry so that you can write 2 equations. As soon as you have 2 equations, and we don't care what problem in this section we're talking about, as soon as you have your 2 equations, solve for x or solve for y, plug one equation into another derivative, you're done, right? The procedure from that point on, it's only tricky to come up with this equation. So now from here, I'll just say solve for x, then plug in. So we had 3 examples that we worked out completely, 2 examples that are worked out partially, and now we're going to change from farmers' problems to something else. You can literally come up with any kind of geometry you want for farmers' problems. You can always make that work. Let's go and take a look at other things that they offer here. Shipping crate. A square-based, box-shaped shipping crate is designed to have a volume of 16 feet cubed. Someone needs to pay, right? This is the packaging engineering right here. So, this is a problem 21, and it says shipping crates. A square-based box. Excellent. I need a square in the base. So we put a square in a base, and it's a box, so we're going to put Well, you can't see these sides, so they should be dashed. Actually, this is a weird perspective. How about we actually do this? It's easier. And then make these guys dashed. Okay, so now it says X and X. It's a square base. That's already constrained, guys. It's a square base, and it's going to have a different height, so we'll call that Y. When you go to Calc 3, you learn Lagrange multipliers. This problem becomes X, Y, Z, right? And my students actually had this on the test yesterday in this classroom. For Calc 3, they had a problem like this, except it's X, Y, Z. Now, to make this problem possible in Calc 1, we impose the restraint that the square base, and that eliminates one variable, because square base is immediately X and X, right? If it's not a square base, then you have X, Y there, and then Z for height. So square base, right? And the volume must be 16 inches cubed. Or feet cubed. I was about to, what inches cubed, really? Like that's 16 inches cubed. Alright, so what do we have? We have the volume. We know what the volume is. Area of the base times the height. So in this case, X squared Y equals 16. That's a constraint. Right? Everything is given. No min-max. It's a constraint that my box must have 16 feet cubed. Why does this come up with the packaging engineering? Well, it has to, because if you are shipping tomato or you're shipping the golf balls or whatever, right? Not everything has to be catered to the shape of the object. Like you can't come up with whatever box for that projector, because if its box is too skinny, projector is not going to fit in it, right? But golf balls would pretty much fit in anything, because they just, you know, arrange themselves into the best way to fit. So for shipping the plastic pallets or mulch or something, right, that can actually fill the area easily, you can have a constraint like this, where we just need 16 feet cubed, and whatever we stuff in it is small enough to kind of fill in the shape. In some other cases, for packaging engineering, the shape of the object is important, right? So the sides of the box would be required, and then the volume will just follow. And then what else do we have? Material used to make the base costs twice as much per square foot as the material in the sides. So now this is going to turn into a cost problem. The money, right, which is important for a company, because you can't just put whatever box you want out there. If you're shipping 100,000 units of something, and you can save $1 per box because of the design, that's saving $100,000, right? We just think small, right, in a household when we are not working for a company. But the company is going to send 100,000, a million boxes, save $0.50 per box. That's $500,000 saved. It's just saving 50 cents in a design of a single box. That's why packaging engineering is extremely important, right? It reduces the cost and also safety of the object to get to the consumer, right? It's not broken and mangled, especially now that we have to ship like half a world away, because we don't produce anything anymore. It's just services and corn and is there anything else? Lawyers, information and whatever Elon Musk does. That's it, right? That's the only American car now designed and produced in the United States, Tesla. Like, where's Ford? Everything is made now in Mexico for like 80 cents a labor, right? Cities destroyed, when the industries moved out, right? All of the manufacturing. So there you go. Let's talk about the cost. It says the cost to make this box. The material used to make the base. Okay, so now we have these issues, and what I need to do is I need to create the wire frame over here. So I'm going to unfold my box. When I open up my box and lay it flat on the ground, I see the base in the middle, and then I have the top attached all the way to the right, and I have 4 sides. So the material used to make the base costs twice as much per square foot as the material on the sides, and the material used to make the top costs half as much. So the order of cost is this. Does it make sense? So there is a cost to make a side times its surface area, and then the base would cost too much. Maybe you have to add wood, right? Wood pallet to it. So it's going to cost much more, right? And for the top, you really, you just need to cover it. You can use a thinner cardboard, right? That it's single layer rather than 5-layer cardboard or whatever. So just make sense out of these things in your head, right? So now I have to come up with a cost equation, and clearly I want to minimize that. So I'm looking for dimensions x and y so that the cost of making the box is the lowest. And this is what you do as a packaging engineer. So now what is the cost equation? Cost. So I am looking for 2 times x squared plus 4 times xy plus 1/2 x squared to be minimum. And now I'm going to just to label these. This is the bottom. These are the sides. And this is the top. And now if I come in here and I put x and x and x and x and y and y, x and x and x and y, you quickly come up with each one of the rectangles is x times y. You have 4 of them, so 4xy's. You have x squared in the middle times 2, and x squared on the outside, which is the top, which is 1/2. So our job is to now minimize this. It says, what are the dimensions of the crate that minimize the cost of materials? Well, how do you minimize the cost of material? You minimize it by reducing the surface area, right? Because the less area you have, less cardboard you are using to make a box. So minimizing surface area, which is the reason why I went with the area equation in the cost, because minimizing the area minimizes the amount of material you're using to make the thing. There is my objective function, it's equal to a minimum, and there is my constraint up there, which is the volume. Remember, we have to fit into 16 feet cubed everything. So now we have 5/2. I'm going to put equations together. 5/2 x squared plus 4xy equals to a minimum. And I have x squared plus y, x squared times y equals to 16. So these are the 2 equations I have to use. I will say y is equal to 16 over x squared. Right, that's my constraint. I'm trying to kill a variable. I'm killing y, right? So now plug in. I'm getting 5/2 x squared plus 4x 16 over x squared instead of y equals to a minimum. And now just shovel through algebra and calculus. 5/2 x squared plus 4 times 16 is 64 over single x, right? Because x and one of the x's cancels. Now, my entire equation is in terms of x, so I am ready to hit this with the derivative, d dx. Derivative of, so 2 drops down and kills the denominator, so it's 5x. Minus 64 over x squared equals 0. When you take the derivative of x to the minus 1, you get minus 1 over x squared. So it becomes, and then 64 is just a constant you copy. So derivative techniques from chapter 3 kick in. And now we need to solve this equation. Now this equation is 5x is equal to 64 over x squared. X cubed is equal to 64 times 5. X cubed equals to, this is 320, right? Is that good, 320? So now what do we do? We take the cube root. Math, 104, 320. I get x needs to be 6.84. Should be just 8. Just 8. Because we had no decimals to begin with, so you go 1 decimal place. Precision. So x needs to be 6.8 feet. Now y is equal to 64 over x squared. No, 16. 16 over x squared. So y is equal to 16 divided by 6.8 squared. I don't like this answer. 0.34 feet. So dimensions are, this box is almost 7 by 7 by 4 inches. 7 feet by 7 feet by 4 inches. I don't like it, but that's what we got. 6.8 by 6.8 by 0.34 feet. I hope all the calculations went. Oh, 64 was supposed to be divided by 5. There we go. 64 divided by 5. See, this is why I love applied mathematics and word problems, right? You get something at the end and it really doesn't sit, right? Why would this box be 7 feet by 7 feet and then 4 inches tall, right? That's 4 inches tall, right? It just seems like really dumb design, right? So you go back and you look for a mistake, and so now your x cubed is 12.8, and then the cube root of 12.8, much better answer, 2.3 feet on x. 16 divided by 2.3 squared is 3, actually. 3 feet. So now, much better answer. 2.3 by 2.3 by 3 feet. And that's that. So this particular calculation shows the box whose design would yield minimum cost to put the box together. times amount of thousands of boxes that you put out, you have yeah. The ladder problem, geometry problem. Ooh, flower garden problem. I like this one. Another nice problem. They give you a flower garden. It could be a pool surrounded by the concrete. Right? You have a pool, you put the concrete thing so if the kids run around, they scrape their knees if they fall, obviously. Right? So this is 2 meters, 2 meters, and then 1 meter, and then 1 meter on dimensions. A rectangular flower garden with the area of 30 meters squared is surrounded by a grass border 1 meter wide on 2 sides and 2 meter wide on the other 2 sides. See the figure. What dimensions of the garden minimize the combined area of the garden and the borders? Great. So I'm going to call the inner dimensions x and a y, because that immediately gives me my xy equals 30 constraint. This is problem 37 in your textbook. On version 2, okay. So we have, I'll put both designations. So we have immediately the constraint inside because the flower garden inside is x times y is equals 30. That's given to us. Now, what is the mathematical formula that I have to write here for a dimension of this? Let me see the engineering mind right now. You can't use 30. I'm looking for the length of that side. 30 is the area. How would I represent the length of the entire garden plus border? Very good. X plus 4. Perfect. X plus 4. So we have this much to be x because it's the same as the length up there. So if this much is x and this much is 2 and this much is 2, the total is x plus 4. And we'll use the same thinking on the side. If this much is y and this is 1 and this is 1, it's y plus 2. Very good. So this side is now x plus 4 and this side is y plus 2. Good effort. So now I know that I want to minimize the total area. So that's going to be x plus 4 times y plus 2 needs to be minimum. Do we all see that? So now I have my constraint, I have my objective function. Go say x is equal to, or y equals x over 30. Not 30 over x, sorry. 30 over x. Plug in. So we have x plus 4 times 30 over x plus 2 equals a minimum. Distribute. X times 30 over x is 30 plus 2x plus 120 over x plus 8 equals to a minimum. 2x plus 120 over x plus 38 equals to a minimum. Hit this with the derivative. 2 minus 120 over x squared, derivative of 38 is 0, equals 0. So all I did is I distributed my FOIL, combined like terms, and once I had equation with a single variable, x, hit that with the derivative of x. And now, solve this. 120 over x squared is equal to 2. 120 is equal to 2x squared. X squared is equal to 60. And x is equal to square root of 60. It should be plus minus square root of 60, but lengths are never negative. So we only keep positive value. Green? Good. So now we have a square root of 60. Again, apply problem. There are going to be decimals all over the place. So we're looking at 7.7 meters. That's about 2.5 times my height. No, 3.5. And to get y, we have our equation up there, which says that y is 30 over x. So 30 over 7.7. 30 divided by 7.7 is 3.89. So 3.9 meters. And now that makes sense. So 7.7 times 3.9 meters is the answer. That's the dimensions. Now, do we really make the money off of the optimization problem for the flower garden? No. As a contractor, you do, because you have a pool. Pool is already set, right? It's a standard size. You want to build the walkway that has these specifications so that you have the minimum amount of concrete. Reduces the cost, right? There you go. You cash in immediately on this problem. Another problem, if you are to flip this on a side, wouldn't this look like a page in a book that you have a text inside and you have the margins on the other side? You want to keep this surface area for the text in the book certain size. You definitely want to minimize the size of the page, because less page, less materials, less raw materials, right? Less cost. Obviously, you reduce that to 0 if you have ebook, right? Which is why the publishers are trying to move now to, right, uploading the book in MyMathLab and so on, right? They're coming up with these million ways, because remember, publishers want to get rid of the books. There are printing costs, there are transportation costs, there are warehouse costs, right? All of that stuff is there. The machines that print the books, they break. It's a lot of stuff. You have to buy the ink and then, manpower to pay the people, right? They want to eliminate all of that and just say, here, it's online book. And certain books that are coming out now for market are only online, right? For the rest, do the minimization problem to reduce the size of the book, keeping the maximum area in the middle for the text so that you can save as much cost. Again, you print 100,000 copies of the book, right? Times the number of pages, times the, little bit of a, just take a book that has, like your calculus book, 1,000 pages, right? Save 1 cent per page is what? $10 on a book, right? Times 100,000 copies is $1 million over this one. So if you are contracted as a person to do this optimization, this problem, what it takes? 5 minutes, $30,000 contracting thing. Here you go, and you have to write the report and actually submit and win the contract and all of that kind of stuff. So there goes your English and communications. To give you $30K for this, for a company is nothing. They save $1 million. Keep in mind that, right? They're not giving you $30K if they're going to save $50K, right? Now, if they knew how to do this, you would need to exist, right? You wouldn't have a job ever. So these are the things that you do as work, and this is why I love these sections, the related rates and this ones, because they directly make you money. You can always, obviously, quit this and do something else, right? But you see directly how this impacts as soon as you're out. You can use this. Now, obviously, there is 300 level courses and 400 level courses when you graduate here and transfer out to build up more. One more of these problems with a different geometry, and that would be it for this lecture. You have obviously about 50 or so problems to consider in a textbook. You can obviously bring the issues to class and we'll deal. This is another one. Let's talk oil, right? Right. So what do we have? We have a seashore over here. Shore and sea. And we're going to have an oil rig in the sea, right? So they can spill it all over the place. And we're going to have oil refinery over here. Rough refinery. And you have options. You can run your pipe underwater, shortest distance straight from refinery to the right. You can run your pipe on the coast and then the shortest distance through the water, because this oil rig is not that far away. Put it out, let's say 5 miles. You don't really want to have a tanker going back and forth, right? Bringing the crude oil. You can build a pipeline. It's not that big a deal, right? But see, the problem is that to build a pipeline underwater, right, a little bit expensive. You gotta have divers that are also, right, good with welding, and you have to weld underwater and support it underwater and make sure that the water can't, right, the currents are not, right, there's issue, right? So it costs much more to put the pipe underwater than to put the pipe on the ground. So now you're thinking, the shortest distance that I can possibly have is to go straight underwater, but that's all expensive piping. Or you can use the cheap one, going on the shore, and then use the shortest possible distance underwater to the rig. So now let's say this is 10 miles, whatever. It doesn't, I'm just tossing whatever numbers. You can put whatever you want. So let's go with 10 miles over here. Now we're going to come up with prices as well. So 1 mile of underwater pipe $500,000? Million?
No.
Million? Guys, these companies have infinite money. It's irrelevant. We can put 7 million. They're still gonna do it. It's just nothing. To set up one of those huge things that produce medications, they have this huge machine that is three stories tall. So it's like a big drum, and they have all these attachments to add ingredients, and that spits out the pills on the other end. So depending on what you put, you get Advil, or you get Tylenol, or you get just whatever. And they have all those nozzles, and then they build building around that. Costs $1 billion to put it up, $1 billion, and then the company just makes 3 of them, because the amount of money they make off of medication is insane. That 1, 2, 3 billion is nothing. They don't even see it. They just write it off. It's like write off someone's vacation. It's like nothing. So what? 1 million. Let's go with 1 million. $1 million for 1 mile. 1 mile on ground. $200, $300, $250. Okay, $250. These things cost a lot, guys. You know those power towers? To put a power tower, those big ones, the metal ones, right? With a set of wires on one side, $100K. Yeah. So when you drive, pass by one of those, and you just look, and you see 10 of those, that's $1 million right there. Like you just see 10 of these in a row. So these things are not cheap. So there you go. That's our cost. What do I want? Clearly, and write that in blood, I want minimum cost. That is what every company is looking for. Minimum cost. Great. Well, I don't have any calculus over here. I have all my distances. This is going to be a joke. Let's go. Number 1, the blue one. I have to use Pythagorean identity to figure out the distance. So the distance is a square root of 10 squared plus 5 squared. That's square root of 125, which is 11 something, right? Square root of 121 is 11. So square root of 125 is 11.18. So that's how many miles you have. So the cost is going to be, it's all underwater. It's 11.18 times $1 million per mile is going to be $11,180,000. So that's the cost. To go all underwater, that's the cost. Then I have the black one. Route number 2. Route number 2 is going to be, the cost is equal to 10 miles times 250,000, because that's 10 miles on the ground, and each one is $250,000, plus 5 times $1 million for the underwater. We have 2.5 mil plus 5 mil for 7.5 mil. Well, let's just write it as a millions. So there we go. That's a $4 million savings, to put it that way, right? Great. Well, you're saving $4 million, why not, right? But then hold on, right? Mr. Calculus is in the room, right? So what do? You propose something else. How about we go up the shore and then cut through the water? You want to optimize you want to find the minimum cost using calculus, and then that is going to go even lower than this, which is what they pay you big bucks for in the company, right? So how do you do this now? Well, you have your so let's go and do this. So we know this is 10 miles over here, but at this split I'm going to call this unknown quantity x, which makes the top one 10 minus x. Does that make sense? Which makes this to be the Pythagorean theorem here. You know what, I'm going to use the red for all of these new ones. So now we have a Pythagorean theorem, capital D, distance underwater. So now, as you can see, what I'm trying to do is I'm trying to go and calculate the distance x plus d, and then x times the cost of $250,000 plus d times 1 million to minimize the cost. Well, that's not going to be a problem, actually. It's going to take us 5 minutes. So route 3. So what do I have for a cost equation? The cost equation here is going to be x times $250,000 plus, and now what's my d? Square root, very good. So it's going to be 1 million times the square root of, and I have this squared and a 5 mile square, right? So it's 10 minus x squared plus 5 squared. Because it's the right triangle right here. Right? That's the right triangle right there. And to find the hypotenuse, the longest side, you take two legs, this one, and you square them, and then you find the square root. So, look, the entire equation is in terms, and I want this to be minimum. I want this to be minimum. So all I need to do is to figure some algebra out over here, simplify it, and we're good to go. 250,000x plus 1 million times the square root, I'm simplifying here, this is 100, and plus 25 is 125, minus 20x plus x squared when you FOIL and add 25. Hit this with the derivative and you're done. You have your x. So hit this with the derivative. ddx. We get 250,000 plus 1 million, and now we have to do this derivative. This is square root, so it's going to be the derivative of this goes on top, and 2 times whatever we have there on the bottom equals to 0. Now the beautiful thing over here is that these 2 will cancel, get a 10 over there. And now I have to solve this equation. $1 million times x minus 10 over the square root of this 125 minus 20x plus x squared is equal to negative 250,000. Multiply both sides by the square root. On the left hand side you have 1 million x minus 10 million equals to negative 250,000 times the square root of 125 minus 20x plus x squared. Square both sides. I mean, move 250,000 over, square both sides, get the x's, get the quadratic equation going. This is called Wolfram alpha. All right. I'm serious. You don't. When you start doing these things, you're not gonna sit there,
No,
right?
I know.
So you fire up Mathematica, which is already on your work computer, and you say solve. And you type in 1 million x minus 10, 1, 2, 3, 1, 2, 3, 10 million equals negative 250, 1, 2, 3 times the square root, so open parenthesis, 125 minus 20x plus x squared, close parenthesis, and that's it. And hit enter. It comes up with complex numbers.
Use square root.
Oh, I forgot to put a square root. Thank you. Raised to 0.5. There we go. So x equals, now we want the approximate form because we don't care about square root of 5 over 3, is 8.7 miles. Great. I just found out that x is 8.7. That's the ground, right? Because that's where my x was. If you go up there and look, you see where my x is? X is the red pipe that goes from the refinery up to the halfway through. So out of 10 miles, I have to go 8.7 miles on the ground. And then my distance formula, which was this 10 minus x squared plus 25, is going to give me underground. Oops, square is on the wrong spot. So this is 1.3 squared plus 25. So now we compute that. It's a square root of 1.3 squared plus 25, close parenthesis, equals to 5.17. 17 miles underwater or under the sea. Now this guarantees minimum cost. So if I go and I say 8.7 times 250,000 plus, this is immediately 5,170,000, right? Because it was times a million. We get 8.7 times a quarter plus 5.17, 7. So this is 7,345,000, right? So what do we save? 7.5.
$250,000.
equals
Yeah.
1.5.
We saved, with 5 minutes calculation, we saved another $150,000. What is for them to give you 20, 30K for that calculation, right? They're saving even more. Now, obviously, if you're working for the company already, that's built into your salary. If you don't compute it, out you go. I mean, you know, it's a stick or a carrot. It depends on which situation you're in. But that's life if you're an engineer. Now, my friend who graduated NGIT last year is working similar stuff for a company in Secaucus. So, there you go. Similar stuff, not this, not for oil companies. It does this for duct work. So you want to minimize the duct length, obviously, to save the length of the ducts in materials as you're building a building. We're talking a single family home. Like, sure, put in extra ducts, so what? It's going to raise the price on a building for $100, big deal, right? But when you have a 26-story, right? You have a 26-story building, each room has to be air conditioned, your office has to be air conditioned, right? You have, who knows, 100, 200, 300, 400 offices, right? The amount of duct, gotta minimize all of that stuff to save on. There we go. Bye. Right? That's the way to make the money.